Hi everyone! Today's video is going to be the first video in our dynamics unit. So today we're going to be going over what a force is, Newton's three laws, what a system is, and how to draw and analyze a free body diagram. Okay, so first, let's get into the definition of a force. Sorry, that was big. So a force is a push or a pull. And we need a force to change the velocity of an object, either if it's stationary to get it to move, or if it's already moving and change its velocity. We will go more over the mathematical part of that in Newton's second law. Okay, so Newton's first law is sometimes called the law of inertia. It states that every object will stay in a state of rest or uniform velocity unless a net force acts upon it. So you may be wondering, why when we throw a ball on Earth, why doesn't it stay at a constant velocity? So this is where free body diagrams come in. So let's say we threw a ball and it gains a certain velocity. The center of mass of the ball, which we will go over more in the next section, is right here, and there's two forces acting upon it. The first force is obvious, gravity, which pulls straight perpendicular down to the path of the ball. We will call this the force of gravity. And the next force is called air resistance, and that's because there are air molecules in the earth which push against the ball as it moves through the air and forms one force against its motion like this. We will call it force of air resistance. Usually in AP Physics 1 problems or AP Physics 2 problems, we ignore air resistance and imagine a vacuum space. So, if we threw the ball in space and there was no other net force on it, there was no gravity or air resistance because it's in a vacuum, it will stay at that constant velocity unless something else in that frame exerts a net force upon it. Newton's second law states that acceleration of an object is inversely proportional to the mass of the object and proportional to the force. This can be represented by the famous equation F, which is force, equals to mass times acceleration. So let's dive a little deeper into what exactly is mass. Something that many people confuse is that mass is also equivalent to weight, but it is not. Mass is not equal to weight. Mass is actually the inertia of an object, and its SI unit is in kilograms. So, for example, if you weighed 100 pounds on Earth, that does not mean that your mass is 100 pounds. Weight is actually a force because weight is represented by your mass times the gravity of Earth. So for example, if I went on the moon, my weight would be much less because the gravity on the moon is less, but my mass will stay constant. Newton's third law states that for every action, there is an equal and opposite reaction. And also, any time a force is exerted on an object, that force is caused by another object. So you may be wondering what exactly an equal and opposite reaction is. So let's draw a quick diagram. Let's say we have a block on Earth, and the surface is on its frictionless. And you use your finger, excuse my drawing skills, to exert a force FH on the block, causing it to accelerate to the right. You may have noticed that when we push on something with our hand or finger, we also feel some sort of push back. That is the equal and opposite force. The block exerts an equal force FH onto our hand or onto our finger, but in the left direction, hence the opposite reaction. And this is true for any force. There is always an equal and opposite reaction to any force. And I'm sure you're all thinking, okay, well, doesn't this cancel out our forces? This is where many people get confused. It actually doesn't, because our hand is exerting the force on the block. The block is exerting a force on the hand. So the net force on both the block and hand is both FH. And so the only force on the block here, if we exclude gravity and friction and things like that, is FH, because the opposite reaction is not exerted on the block. It is exerted on the hand. So Newton's third law comes to use especially in normal force and what we all know as weight. We will go over normal force and weight a little bit later after I explain systems, equilibrium, and how to draw a free body diagram. Okay, now let's talk about systems, equilibrium, and free body diagrams. So a system is essentially a piece of the universe, or however much objects we choose to be in a system. Usually physicists define a system in a way that helps their problem be solved easier, which we will go into when we get a little bit more advanced. In a system, when we're solving dynamic problems, we need an inertial reference frame. So, an inertial reference frame is a frame in which is not going acceleration. So for example, if I had this ramp and a ball rolling down the ramp is not accelerating while the ball is. I could take this to be my inertial reference frame and my system to consist of the ball and the ramp, or I can choose it to be the ball, the ramp, and the earth, and so on. Okay, let's imagine that this block is you, and all your mass is condensed at its center of mass. We know that since we're on Earth, we have a force pulling down on us, which is going to be mass, your mass, times the gravity of Earth. We know this because of Newton's second law, where F equals ma, and mg is going to be force of gravity. And now we can use Newton's third law. We know that for some, we don't know what force, but we are exerting some force onto the surface. We don't know what force that is yet. We call this normal force. And since Newton's third law has an opposite and equal reaction back to the object that exerts the force, there is going to be another force, N, upwards. Now, how can we figure out this N? When you're standing on Earth, you're stationary. This tells us that our net force is 0. And if our net force is 0, that means considering up to be positive and down to be negative, then N minus Fg has to be 0. This tells us that N, which is normal force, is equal to Fg, which is equal to mass times gravity. And that is how we calculate normal force. Keep in mind that normal force is not always equal to your weight. And this is because if you're in an accelerating reference frame, sometimes this can change. We will go over this in some future videos. So this is how a scale reads our weight. Let's draw another diagram using a scale. So I'm going to draw the green as our scale right here. And This is our center of mass. Okay, first we know that Earth is exerting the gravitational force Fg, which is equal to mg. We know that since we are sitting atop of the scale, we are exerting some force we don't know yet, which we'll call normal force. According to Newton's third law, there is going to be an opposite and equal reaction to the force we exert on the scale back to us. So the same force will act N, but upwards. Again, considering upwards positive and downwards negative, N minus mg is going to give us our net force. Since we're stationary when we stand on a scale, we know that our F net has to be 0. That tells us that N equals mg. A scale reads this normal force, and that is how it reads mg, which is our weight. Later, when we go into some more advanced normal force problems, you'll see that if we're in an accelerating reference frame, sometimes the scale can show heavier or lighter of a weight depending on the physics. We'll go over that later. Okay, this ends today's video. And in our next video, we're going to be learning about contact and non-contact forces such as friction. And we're going to be practicing a few of these equilibrium problems using Newton's second law and also using Newton's third law. Thank you so much for watching.